This case study of a fertilizer manufacturer that used multiple linear regression to minimize the waste streams from their process is brought to you by JMC Data Experts. A fertilizer manufacturer uses a production process that required milling feed rock to a fine powder, treating it with acid and filtering out the final calcium phosphate fertilizer product. Many process variables, as well as the rate of two waste streams, are recorded each day. Their goal was to learn the relationships between these variables in order to minimize the waste streams from the process. Multiple linear regression is an analysis tool that allows you to develop a model for the relationship between input and output variables of a process. That model can then be used to find the process conditions that optimize the output variables. The process shown here had many inputs, such as the rate of rock feed to the ball mills, slurry density, flow rates of sulfuric and phosphoric acid, and the rates of several recycle streams. The manufacturer's goal was to minimize the two waste streams from the process, because each 1% mass flow to landfill cost the facility roughly $300,000. This schematic of our analysis shows the 13 potential predictor variables and our two waste stream rates as the response variables. One of the predictors, blend, is a categorical variable. It indicates the mine source of the rock fed to the process. When viewing the size of the waste stream over time with the blend identified, we see some variability with changes in blend, but the majority of the variability is over time. Because of this, we decided to remove blend from the analysis and focus on the remaining 12 predictors. When using regression analysis to discover the relationships between your process variables, there are 3 important steps you need to take to maximize your success. First, if you have predictor variables that are correlated, they will essentially occupy the same space in the analysis, and this can alter the results for each variable. Typically, all but one predictor of our correlated group is removed from the analysis. Let your process expert select the one variable they believe most likely has the strongest effect. Secondly, process variables often interact with each other, so you should test for interactions effects in the regression analysis. This can lead to what might appear to be too many model terms to analyze, in this case 66 two-way interactions and 12 main effects. However, using stepwise regression makes handling a large number of terms in the model reduction much easier. Finally, coding high to low predictor settings as +1 to -1 minimizes correlation of the regression model terms. This is the same technique that is used in DOE analysis. Using this approach with the regression commands will reduce the confounding of effects that commonly occurs in historical datasets. Let's have a look at our results. Our mathematical model for waste stream 2 shows a strong effect of slurry solids, acid-rock ratio, and the interaction of the two. Using the contour plot of our model, we see that at a high acid-rock ratio, we can get either a high waste stream at 5.6% if the slurry solids are low, but a low waste stream of 2.1% if slurry solids are high. The difference of 3.5% was a great result for the engineers as they moved their process to the high-yield process settings. With each percent reduction worth about $300,000, the final cost savings was roughly $1 million per year. If you would like to use multiple linear regression to improve the performance of your process, or if you have any questions about this case study, contact us at JMC Data Experts.